Good morning, doctor.
So we will start today problems on chapter 7 and 8. Okay. We start first with the first problem. A disc of 40 centimeter in diameter and 5 centimeter in thickness is cast of pure aluminum in an open mold casting operation. First, aluminum melts at 660. This one we did it already, you know? Yes, we did it already. This one. So let us do the second
But
problem.
doctor,
Yes?
in the first question, I didn't understand the equations we used. I rewatched the recorded session, but I can't remember we took these equations before.
Okay. Look, if you are industrial engineer, maybe you didn't face these formulas before, so I will repeat in brief. Okay? Look, whenever you have, if you want, let me go back to the course material, so it will be easier to explain it for you. It is chapter 7, so let me open the PDF. Do you see the PDF now or not yet?
No, it's a blank screen.
Yeah, just 1 minute. Still black screen?
It's gray now. I can't see it.
Fabiola, 1 minute.
I think it's loading or something.
Okay.
Doctor, maybe if you try closing the other tabs بيصير أسرع.
Yalla, it opened. Yeah. I think you see it now?
Yes, it's working.
Okay. Yeah. Look, here, if you look at the solidification graph here, you can understand what are the different phases for pure metal and for an alloy. So let us start with pure metal. So if you look at this graph here, what we have, you have several phases. So in this graph, we are going from liquid to solid. Now in the problem we did, we are doing the inverse. Just we are going from solid to liquid. But what is the idea? Here in this example, in the problem, they told you that you were at room temperature. Okay? And you will heat your system. Okay? So in a first phase, you will go from solid to liquid. When you go from, you will first heat your solid. Okay? So in a first phase, you just have solid material. When you have one phase in your system, when you give heat, what will happen? The temperature will increase. Okay? So we say that if we have here, we are doing the analysis for a pure metal. So first, in the first step, if you want to heat it, okay, I want to heat a pure metal, okay, I should know what is the initial state of my metal. If my initial state is solid, okay, this means that when I provide heat, what will happen? The temperature will increase. Okay, so first the temperature of the solid will increase, and therefore when the temperature increase, I say that my heat, okay, is converted to sensible heating. So why we say sensible? Because I am seeing that the temperature is increasing. Okay, so this is called sensible heating. And the formula for sensible heating is the following. Okay, when you provide heat, what is the unit of heat? Heat is in, you know, what is the unit of heat?
Heat, the unit.
Joule, okay? Joule, energy.
Oh,
Energy,
it's
okay?
energy. Okay.
It's in joule, yes, it's in energy. This energy is increasing the temperature, so we call it sensible heat. And it's calculated as the mass, which you are heating in kilograms. The specific heat, C, is, we call it CP, specific heat. In general, yani we consider it at constant pressure because the pressure is not varying. So just call it C. It is specific heat. Okay, and its unit is in joule per unit mass per kilogram per delta T, per variation of temperature. Sometimes we give it per Kelvin, sometimes we give it per degrees, but as I told you before, it's the same because delta T in Kelvin is equal to delta T in degrees. Okay, what is the meaning of specific heat? If you look at its unit, if I tell you a material has a specific heat of 1000 joule per kilogram per Kelvin, this means what? This means that you should provide 1000 joule in order to heat 1 kilogram, in order to raise 1 kilogram temperature by 1 Kelvin. This is the mean of specific heat. How much heat should be provided to 1 kilogram of this material to raise its temperature by 1 Kelvin or 1 degrees? Okay? Times delta T. So C is a characteristics of the material you are using. And delta T is the temperature variation. Okay? So in case you are going from, in case you are heating, delta T is positive. This means that your material is absorbing heat, which will increase its temperature. In case you are cooling, delta T will be negative because you will go from highest temperature to a lowest temperature. Okay? So delta T is always T final minus T initial. Okay? Now, so the first step is to heat your metal until reaching what? At what instant sensible heating will stop? When you start phase change. So when you reach a critical temperature, which is called melting temperature. Okay? The melting temperature is the temperature at which you start to observe change of phase from solid to liquid. So if you are heating, you will go from solid to liquid. If you are cooling, you will go from liquid to solid. So this graph can be valid in two cases. You can, in case you are cooling, you start from the pouring temperature until complete solidification. So here you have first liquid cooling, then you have a change of phase from liquid to solid, then you have solid cooling. And in case you are moving in the opposite direction, so before, at the initial state, your metal is solid. You need to heat it before pouring because you cannot pour your metal in the solid state. So first you should convert it to liquid to be poured in your cavity. Then when it will take the cavity shape, you will keep it, you will cool it until having total solidification. Okay, this is why these processes are called solidification processes, because they rely on first melting the solid in order to be poured in the cavity, and once it takes the shape of cavity, we keep it to cool in order to get the final product. Okay, so now in the problem we are doing, we are working in the other direction. We are first heating to be able to reach the pouring temperature. So we were initially at the ambient temperature. Since we are far first from the melting temperature, the first step is to heat our solid until reaching the melting temperature. This is why you will say that in a first stage, the sensible heating is MC delta T. And what is T final and T initial? T initial is the temperature at the start of heating, which is the ambient temperature given. And T final of the first phase is when you reach the melting temperature. Because once you reach the melting temperature, you will start to have change of phase from solid to liquid. Okay? Now, What will happen in the second phase? In the second phase, initially you had 100% liquid, and once you reach the melting temperature, you will start to have transformation from liquid to solid. Sorry, from solid to liquid, I mean. Okay, because you had first 100% solid, and now I reached the melting temperature, so I can now have change of phase from solid to liquid. So at the end of the melting phase, you will go from 100% solid to 100% liquid. In this zone, you have two phases. Okay, whenever you have mixture of phases, when you have a pure alloy, you will maintain constant temperature. So this region is called, this is the change of phase. Okay, and since it's a pure metal, the temperature will remain constant, T constant. So since I don't have any more temperature increase, my energy that is absorbed will be transformed into another type. Okay, instead of being transformed into sensible heating, which will increase the temperature of my metal or any fluid or any solid I am talking about, then what will happen is that this energy will be taken by the molecule to break bonds, okay, or to reduce bonds if you want, because in solid bonds are very strong and molecules are very close to each other. While in the liquid state, they can move more they have more freedom in motion. So the attraction between molecules is reduced. In order to, if you want to have rupture of these strong bonds, you need energy. This energy will lead to transformation of state instead of increase in temperature. This is why this energy will help you to go from solid to liquid state, but without increase of temperature. So in this case, we say that the heat, when we have two phases, and I repeat, we are considering a pure fluid, pure metal. Okay, so one, you have just homogeneous structure, you don't have different composition. Okay, so when we have two phases of a pure metal, then heat is absorbed in latent form. Okay, heat is absorbed in latent form, and then the equation of it will be Q latent equals to the mass times what we call here latent heat of fusion, because you need to provide a certain heat to go from 100% solid to 100% liquid. Okay, and in case you are moving in the opposite direction, so if in case you are freezing, you are this is called, you can say that during this phase heat is lost, while if you are heating during this phase heat is gained. Okay, so now LF, also heat of fusion, is a characteristic of the fluid, of the metal. Okay, so we will provide it for you, so you can calculate easily in this way the latent heat. And the latent heat is in joule per unit mass, joule per kilogram or joule per gram. And this means that what is the amount of heat needed to provide 1 kilogram in order to change its phase from 100% solid to 100% liquid. Okay, after this, once you have 100% liquid stage, in order to heat to the pouring temperature, then now you are in a liquid heating when you go up, and then it is also a sensible heating, and it's given by mc delta T, but now delta T will be T pouring temperature minus T melting. Okay, is it clearer now?
Yes, it's clear. Thank you.
Okay, so let us go back to the problems.
دكتور عندنا شيء نعمل calculation للالوي او بس pure metal؟
هلا للالوي it's little bit more complex. اوكي، هلا للالوي اذا شيء فيهم يعطوكم I will tell you what they can give you. يعني for the alloy ما حفت لكم فيهم لانه it's little bit complex. يعني نحن كمان في عالم مش اخذه thermodynamics, so ما حأعطيكم for an alloy, don't worry about it. إذا كان composition, just you should understand the concept, بس ما حنفوت ب details calculation. Okay? يعني here, just for an alloy, we should say that, let me go back. For the alloy, what is changing is that during, if you want, during the change of phase, we don't have constant temperature. Why? Because you have a mixture. So what is happening is that the change of phase of the first composition is different than the change of phase temperature of the second composition. This is why you have a range of temperatures for which you have freezing or melting. So if I am heating, the change from solid to liquid will begin at the melting temperature, at the lowest melting temperature, okay? And it will end up at the highest melting temperature, because you have two components. This is why melting phase will not be at constant temperature. It will be at variable temperatures. And just you should know the behavior of the graph, but we will not go over calculation details, okay?
Okay, doctor.
Okay. Now, going back to the problems, a disc of 40 centimeter in diameter and 5 centimeter. Oh, Jean, no, not this one. Okay. A flat plate is to be cast in an open mold whose bottom has a square shape that is 200 millimeter by 200 millimeter. The mold is 40 millimeter deep. A total of 1 million millimeter cube of molten aluminum is poured into the mold. The solidification shrinkage is known to be 6%, which is a volumetric contraction, not a linear one. In general, they will tell you volumetric or linear contraction. When they say volumetric contraction, this is the reduction in volume. When they say linear contraction, this is the reduction in each dimension. And aluminum has a 1% linear shrinkage due to thermal contraction after solidification. So here, if you remember, we talked in the course material about two shrinkage steps. The first one is directly after pouring, which is called, in general, in this phase, you have a reduction in height in general. And after complete solidification, you have linear shrinkage in all dimensions, okay, due to the thermal contraction. So let us do the analysis step by step. So first, what we have is, we have initially a flat plate to be cast in an open mold. So when we say open mold, then in general, the shape will not be complex, because we don't have, in general, when we have open molds, the geometry is not complex, because if you have, consider, for example, if you want to do this shape. In open molds, it's not possible, because if you want an open mold, what you do is you reverse your mold and you get your final cast, and it should be able to go down without obstruction. If you have this shape, for example, you cannot reverse it. Why? Because here, ما حيخليها تنزل, these parts here. So in general, for open molds, we have very simple geometries. Okay, disc, plate, flat plate, etc. Okay, whenever I have complex geometries, here what I do is I use a mold that can be, it's a closed mold that at the end I will open it and I will get to my total part. Okay. So now here, pay attention for the given. They said that the mold is 40 millimeter deep, بس مش يعني إن إحنا we will fill it completely. يمكن you want, you can play with the thickness of your cast. هلا what is fixed will be the base dimensions, but for the height you can fill it till the end, or you can just fill a small part if you want to reduce the thickness. Okay, so to know what is your thickness, you need to know what is the amount of molten metal that is poured into your mold. This is why they gave you this information, because if you don't fill your mold to the end, then you will have a reduced thickness. You will not end up with a thickness close to 40 millimeter. You will have a lower thickness. So here, this is why they gave us the initial volume of molten metal. From the initial volume of molten metal, what can we deduce if we know the base area?
الهايت.
Exactly. We can know the thickness of the plate we want to design. Pay attention that always these are not the final the final dimensions, because you have shrinkage. So here just we know the initial dimensions. The initial dimensions are 200 millimeter for each base. It's a square base area, so 200 by 200. And in order to get the initial thickness H0 or the initial height, okay, we will use the volume of the molten metal. So we can say that V0 is equal to the base area times the height. It's equal to 200 times 200 times H0 equals to 1 million, which is the volume of the molten metal. Okay. Now, from this relation, we can get that H0 is, pay attention for units, please. You have the volume here in molten metal is given in millimeter cube. So have all your dimensions in millimeter. Then H0 will be in millimeter. You will get 25 millimeters. So as you can see, it is much lower than the total depth of the mold. So here we didn't fill completely the mold. Okay. So this information is just a tricky information, because some will not pay attention and they will consider that the initial height is 40. Okay. Now, to continue, once we know the initial dimensions, we will see after each step of shrinkage what will happen.
ايه حبيبي ايه يا روح ايه شو
Guys, please can you mute your microphones when you don't
يعني
ask
راح نستشفى الى باي بابا.
Please mute your microphones when you don't ask questions, please. So this is the initial height H0. Now, in the first step, we will have solidification shrinkage. Okay, which is due, as we said, if you remember, we said that in the first step, once we pour the metal, what will happen is close to the walls will have formation of solid. And then because of cooling of the molten metal, we will have increase in density, which will lead to reduction in volume. But since we are still, we consider that the fluid will tend to fill the base, okay? And that molten metal can be supplied, if we continuously supply it, we can ensure that in the first phase, we will not have reduction in base dimension. We will only have reduction in height, okay? So here, this is what they told us at the end. They said that if the availability of molten metal in the mold allows the square shape of the cast plate to maintain its 200 millimeter by 200 millimeter dimensions until solidification is completed, determine the final plate dimensions. So what they mean by this sentence is that before having 100% solid, since liquid is already present here, I can still also, if you want, I can still supply it. Then I can ensure a base area of 200 by 200 that will not change in dimensions. Only what will change is the height. Okay, I will have reduction in height due to shrinkage effect, due to increase in density. So during a first phase, only the height will change. And since they gave me the percentage of reduction of volume and the base is not changing, then the percentage of volume reduction is equal to the percentage of height reduction. Okay, so I can directly say here, since the base dimensions are not varying, so reduction in height, H final, is equal to 1 minus 6%, so 1 minus 0.06 times H0, okay? So this will give me 0.94 of H0. Here, if you want, I will say not H final, I will say H1, so after the first phase, okay? If you want, another method will be the following. You can say I calculate the volume at stage 1. Volume at stage 1 is 0.94 V0. Okay, and since the base is not changing, so I will write that it's equal to 0.90. So V1 is equal to the base, which is the same area of the base times H1, while V0 can be replaced by area of the base times H0. So as you can see, area of the base will be simplified, and I will deduce that H1 is 0.9480. Okay, so always when the base is not changing, then the reduction in volume is equal to the percentage of reduction in height. This will allow me to calculate the new height after the first phase. Okay, so the new height is 0.94.
Doctor,
Yes. Yes, tell me.
could you repeat ليش أخذناها بس على الهايت مش كلها؟
Yes, because look, they said that before complete solidification, okay, the availability of molten metal in the mold allows the square shape of the cast plate to maintain its 200 millimeter by 200 millimeter dimensions. How you can understand this? Look, when you have
okay,
a liquid tends to fill the reservoir. So it will try to fill the base. Always it will try to fill the base, but the height can be reduced, okay? Because a fluid, you know, will take the shape of the container, not like the solid. So until complete solidification, you will have that, since the fluid is already still here, it can fill the base and just the reduction will be in height. Once you reach complete solid, then when you start the thermal contraction, when you have solid cooling, the density will increase, then the shrinkage will be in all dimensions because a solid will not tend to fill, to take the shape of the container. Okay? Okay. So now, this is the value of the new height after phase 1. So we finished from the first shrinkage phase. Now in the second shrinkage phase, which is due to thermal contraction after solidification, we have linear shrinkage. So shrinkage will take place in all dimensions. Okay. Now, during the second the thermal contraction phase, they can give you the linear shrinkage, or they can give you the volumetric shrinkage and you deduce the linear one. Because you know that in the final phase, all dimensions will be reduced. Okay. And I can correlate the volumetric shrinkage, which is the volume reduction, to the linear shrinkage. How can I do it? I can say that if they gave me the volumetric shrinkage, it means what? It means that V2 is equal to 1 minus volumetric shrinkage times V1. Okay. And if they give me the linear shrinkage for each dimension, then I can say that it's equal to 1 minus the linear shrinkage cubed. Why cubed? Because each dimension is reduced by 1.3%. Okay? And if you want to do it in detail, then you will have the 200 is multiplied by 98.7%. Okay, and the other dimension 200 is also multiplied by 98.7%, and the height is multiplied by 98.7%. So you will have in total, if you want, 98.7 or 0.987, since it's 3 times, so cube times V1. Okay, this is why I can say that the final volume is 1 minus the linear shrinkage cube, because it's applied on each dimension, times V1. Okay, and I can deduce then what is the volumetric shrinkage, the total shrinkage of the volume, from this relation. Okay, because once I find V2, to find the volumetric shrinkage, I say 1 minus volumetric shrinkage times V1 equal to V2. I get the volumetric shrinkage. So from this formula, I can deduce that 1 minus volumetric shrinkage is equal to 1 minus linear shrinkage the power 3. Okay, so you can go from linear to volumetric shrinkage easily. If you know one of them, you can get the second. Okay, here they directly gave me the linear shrinkage. So for each dimension, I have a reduction of 1.3%. So now to find my final dimensions, the final dimensions of my plate, I can say that initially for H2, it is H1 times 0.987, which is equal to H1 is already reduced. Yani I have in total 0.94 times 0.987 times 500 millimeter. So this is the final height. While for the base sides, so for each base side, I have A equal to 200 millimeters times 0.987, because the base will only undergo shrinkage in the second phase. Okay? Any question on this? So we can see here together the details of solution. Let me check. Okay. So here, in initial step, they got the starting height. And then from volumetric solidification shrinkage, they got the new volume. And then they divided by the base area. And here they did it in a more complex way. They could directly say that since the base is not changing, then the height is reduced by 6%. So you will get, of course, the same result. You get that the height after phase 1 of shrinkage is 23.5 millimeter, while the base maintains its dimensions. And then in the second step, to find the value of thermal contraction, so after thermal contraction, each dimension is reduced by 1.3%. This is why you multiply the dimensions after phase 1, each by 0.987, which correspond to 100% minus 1.3%. So you get that for each side you have 200 times 0.987, which is 197.4 millimeter, while for the height it's 0.987 times 23.5 millimeter, which is already reduced from 25. So you get the final height and the final dimensions of your base. So let me open a new meeting, because this meeting will end soon, to start the other problem. Okay.